So far, we have done two examples determining the slenderness of a column. The two examples are referring to the same column, except that the structure conditions are different. The example D here assume that the structure is braced, whereas the example E assume that the structure is unbraced. The rest of the details are the same in terms of the specifications, dimensions, as well as the loading acting onto the column. We shall now proceed to the next question, asking us to compare the calculated result of the braced and the unbraced structures as obtained from the two questions that I mentioned previously. You are asked to state your findings. To solve these questions, first we will need to compare the calculated result from the two questions. The result from the braced structures is obtained from question D, whereas the unbraced structures we obtain from the question E. If you look at the calculation steps comparing the two questions, you will find that anything related to the properties of the columns and the beam, particularly the stiffness as well as the relative column stiffness, these are going to be the same regardless the structure is braced or unbraced, as they are governed by the sectional properties of the columns and the beam, as well as the setup of the column. The differences start with the effective length. Since the equations used to determine the effective length differs, you use these equations for the braced structures and you use these equations for the unbraced structure. You have the effective length in the major axis and the minor axis. The two value differs due to the orientations of the beams at the joint, as well as due to different stiffness of the column when the columns is of rectangular shape. When the arrangements of the beam in the primary and the secondary are the same, and when the size of the beams are also the same throughout, plus when the column dimensions are in the square shape, you will get the same set of case in the major and the minor axis, which subsequently will lead to the same effective length in the major and the minor axis. When the equation used to determine the effective length differs, now the calculated effective length will be different between the braced and the unbraced structure. The radius of gyrations is the geometrical property of the column. It is determined by moment of inertia as well as the cross-sectional area of the column. This property is not affected by the type of the structures. Therefore, the values remain the same. The slenderness ratio is calculated by dividing the effective length with the radius of gyrations. That means you are talking about dividing this with this. When the effective length differs, the calculated slenderness ratio differs. Next, it will be determining the slenderness limit. For the unbraced structure, the slenderness limit it will be determined by this equation. There is no doubt about it, since the other two equations are not applicable to the unbraced structure. As for the braced structures, the slenderness limit can be determined by either of these three equations, subjected to the response of the column, as well as the moment acting onto the column. I indicate here there are two values of the slenderness limit subjected to the load case that you assume. We talked about this previously. If you assume this is the load setup for this column, that means you are anticipating such a response of the column, leading to you using these equations, and this value is obtained. Now if you assume this load arrangement, that means the anticipated column response, it will be something like this. As a result, this equations is used. That will give you higher slenderness limit. As you can see here, it is also possible for the braced structure to use these equations. This equations is not unique to the unbraced structure. In fact, the usage of the equations are very much governed by the response of the column. Only that such a response normally seen in the unbraced member, and it sometimes can also be seen among the braced member. This leads to us an understanding. Now the slenderness limit, to the first principle, it is not really governed by whether the structures is braced or unbraced. When we talk about the unbraced structure, we use this, and the braced structure, we use this. These are the outcome of the classifications, which has already been made simplified for students to comprehend in the case that they have difficulty understanding the fundamentals. Now if we go back to the fundamentals, everything goes back to the response of the column. This is an important message that you should get out of this video. Next, we talk about the classifications of the column. This is determined by comparing the slenderness ratio against the slenderness limit. That means you are using this compared to the slenderness limit for you to conclude whether the column is short or slender. Let's say now we disregard this load case just to demonstrate the implications of the type of the structures over the same column to the types of the column, whether it is short or slender. Now having this result summarized in the table, we shall look into the findings. For the same dimensions and the setup as well as the loadings acting onto the column, it seems that the unbraced structures will have longer effective length than the braced structures. If you see the numbers here, the effective length is normally greater than the actual height of the story when it comes to the unbraced structure. As for the braced structures, the effective length is normally smaller than the story height. Having this understood, next time when you deal with any of the examples calculating the effective length, more or less you will have an idea whether your calculations is logical or not. If you calculate the effective length for the unbraced structures smaller than the story height, most likely something is wrong. Similarly, when you find that your effective length for the braced structures to be higher than the story height, something might be wrong also. If you find this very difficult to imagine, you may refer to the typical sketch here. This is a typical unbraced structure. You can see the response of the column is not restrained in the horizontal directions from one end, whereas the braced structures can be represented by this diagram here, where you have horizontal resistance in terms of the movement of the joint. Now if you see these three categories here, the effective length are normally smaller than the actual length of the member. Now, because of the longer effective length for the unbraced structures, this will lead to higher slenderness ratio. You see the effective length here is greater than the effective length here. As a result, your slenderness ratio shall be greater than the braced structure. Since we are talking about the same column with the same dimension. Next, the unbraced structures are more likely to be slender column than the braced structure. This goes back to the response of the column. Unbraced structures normally will end up with these equations. As for the braced structures, you can have either of these three equations as your slenderness limit, subjected to the response of the column. The most critical state it will be this equation. That means the unbraced structures is more likely to have the slender column, especially when the slenderness limit is relatively small. Next finding. In this case, the slenderness ratio at the minor axis is normally higher than the major axis. This happens in both braced and unbraced structure. You see the minor axis having the bigger slenderness ratio. Same goes to the unbraced structures here. If you look into the calculation steps, although the major axis having the greater effective length, because of the rectangular shapes of the column, 300 times 150, the aspect ratio is relatively large. You will get a huge difference in terms of the radius of gyrations. The radius of gyrations is governed by the moment of inertia. From your calculation step, the moment of inertia of the column, it will be the BH power 3. When the B is 150 and the H is 300, the moment of inertia in the major axis, it will be significantly larger as compared to the minor axis, where the B now is 300 and the H is 150. This gives us an idea. The orientations of the columns is very important in terms of the stiffness as well as in terms of the capability to resist moment. Now, because of the aspect ratio of the column, the slenderness ratio, it will be more critical in the minor axis. This is very much governed by the column aspect ratio. Now, by comparing these two examples, we gain better understanding in terms of how the slender and the short columns are computed. This gives us some ideas when come to the real applications of the column. In principle, slender column will have additional second order moment. And because of this second order moment, the moment to be taken by the column, it will be relatively larger than the short column. As a result, you might going to need more reinforcement bar as compared to the short column. In practice, steel bars are more costly than concrete. In terms of the calculations, slender column, it will be more tedious than the short column. Normally, engineers will prefer to have the short column instead of the slender column, so that they can do a quick checking in terms of their design by simply adding up the sectional area of the column, which ultimately will affect the radius of gyrations, or by simply deciding the type of the structure, whether it is braced and unbraced. Engineers can decide whether the column is going to be short or slender. Now you know the principles and know how it works for you to adjust the column, skew towards the category of short column. for simplicity in terms of the design. I guess this is the greatest benefit that you can learn from this example here.